Hello, welcome to lecture 18 for Math 155. Today we're going to be reviewing one-dimensional differential equations, or ordinary differential equations, which can also be referred to as ODEs. The reason we're doing this is because we're going to be building systems of differential equations. So again, going from one dimension to multiple dimension, as is the theme throughout this course. So before we get to those more complicated systems, we're just going to focus in on those one-dimensional differential equations and just review some things that you would have previously covered in Math 154. Okay, so just to recap them, what is a differential equation? Well, this is an equation that contains an unknown function and one or more of its derivatives. So for example, we might write down something like dy dt is equal to y. This is a differential equation in y. It has first order because the order of the derivative, the order of the differential equation is the order of the highest order derivative. So we just have dy dt, so we have order 1 here. We might also see something like d2y dt squared is equal to y plus 4 plus e to the y, say. The highest order derivative is 2. So this is a second order differential equation. We can see different notation as well. So you might see things like, for example, dx dt is equal to something. You might see x with a little dot over it is equal to something. That would be a first order derivative. You might see an x prime. These are all fine for notations. We might see x double dot over the top to indicate that this is a second order derivative. Okay, so there are lots of different types of differential equations. Just to summarize them, we have autonomous differential equations if, say, we can write dy dt is equal to f of y, where there is no time dependence in our function f. This compares with the non-autonomous differential equations, we would be writing dy dt instead is equal to f of y and t. So this function here depends on time. So this is a non-autonomous differential equation, and the first example is an autonomous one where there is no time dependence in f. We see that differential equations are separable if we can write dy dt is equal to f of y, let's say g of t, because then we can separate these out and integrate them. This has solution given by the integral of dy over y is equal to the integral of t with respect to t. So this is an example of a separable differential equation. We can have linear differential equations where our dy dt is just some linear function of y, say y plus 4. And a nonlinear differential equation is one where we can't write our y in this simple linear form. Say we've got y squared, or we've got an e to the y. So these are various different types of differential equations that you might come across. So it's good to be familiar with the different ways in which we describe them, and also that links into how we can solve them as well. We're going to focus a little bit on how we derive differential equations and where we use them. A really common use for differential equations is to model population growth. So we can do this using just a one-dimensional ODE. There are many cases where we might want to use more than one dimension. We'll get onto those in a couple of lectures' time. So suppose we want to model this population of yeast. You can read the blurb in your own time. But what we can do is we can say that the population at time t is given by capital N of t. And we want to, rather than work out this n of t directly, we want to think about how n of t changes over time through different biological processes. So we can think about the population size at time t plus h, so a little bit further on in time, being based somehow on the population at time t, plus the number of cells, our yeast population, created between times t and t plus h, minus the number of cells that die. again, between t and t plus h. So one of the simplest models we can do is to assume that our births and deaths are occurring at constant per capita rates. So per capita means per individual in the population. So if we have a per capita birth rate of beta, and there are n individuals in the population at time t, and we're going to have a time interval of length h, then the number of births between t and t plus h is going to be approximately equal to beta times n times by h. Likewise, if we have a natural mortality rate of mu, then if this is a per capita rate as well, then we're going to have approximately mu times by n times by h deaths between time point t and t plus h. So this is our birth rate. This is our mortality rate. These are both per capita. So now what we can do is we can write this equation as n at t plus h minus n at t. So we're just taking that n of t over to the other side is going to be equal to beta times by n at t times by h minus mu times by n of t h times by h. So this is just the births minus the deaths. And then we can divide through by h on both sides. And we can write beta minus mu, so we can take this out a factor of n of t. And we can write this beta minus mu as just one parameter. So beta and mu are just constants, so we can replace beta minus mu with another constant r. So if we then take the limit as h tends towards 0 of this term on the left-hand side, so the limit of this n of t plus h minus n of t over h, this is going to equal r nt, and we can write this as just a derivative. So if we think about our population changing from one time step to another, and then make that time step get shorter and shorter and shorter, we end up with a derivative. So in this case, this happens to be a separable differential equation, and we can solve this with this explicit solution here. So the population at time t is equal to n naught, where n naught is our initial condition, so the number of individuals in the population when t is equal to 0. So we have the n naught times by e to the rt. So this gives us exponential population growth or decay, depending on the value of r. So this n naught is our initial condition, and the r tells us what the population is going to grow or decay. So this equation here is a general solution to our differential equation, our ODE, which is here. So let's talk a bit more about what it means for a function to be a solution to a differential equation. What it means essentially is if we take the derivative of that function, then we end up with our differential equation. Okay, so if we think about our model dn dt is equal to r of nt, so if we take our derivative of our function, so let's take d by dt of our proposed solution function n naught e to the rt. This just gives us n naught r e to the rt, which we can rearrange to be r times by n naught e to the rt, which is just r times by n of t. So we see here that our solution n naught e to the rt satisfies our differential equation when we take the derivative of it, and therefore it is a solution. Okay, so what is n naught though? Well, we said on the previous slide that this is our initial condition, and that simply means where we're starting off here when t is equal to 0. So we could be starting in principle at any of one of these points here, and each of these gives a different solution trajectory over time. So depending on the initial condition that we have, it will give us a different value at n of t. And that should make sense, because if we start off with a much bigger population, then we should end up with a much bigger population later on, if we just have, say, exponential growth. Okay, so we refer to a specific solution to our differential equation as an initial value problem. So we need to have both our differential equation and an initial value for the population. And then that means we go from our general solution to a specific solution. So just one of those trajectories rather than this family of trajectories. Okay, so this is an example of an initial value problem where we have both our ODE and an initial value. And using that, we can find our general solution potentially and then plug in our value of n at time 0 to get a specific solution. So we know that we have n of t is equal to n naught e to the rt. And we know that n at time 0 is equal to 12. If we substitute n at time 0 into our equation above, then n times 0 is just going to be equal to n naught e to the r times by 0, which is just n naught. And that implies then that n naught is equal to 12. So our solution is just going to be n of t is equal to 12 times by e to the rt. So we've been able to use that initial value to get a specific solution to our system. Now, often in modeling, we don't necessarily care about the exact dynamics at a particular time. What we tend to care about is what's going on qualitatively. So, for example, are there any particular special values that our system might take on that determines certain behavior? What happens if we start near certain values? For example, in this population, does the population grow or decay when you start near those values, and what values does it tend towards? What happens in the long term as well? So what happens as t gets large? And that means that we tend to focus on equilibria and stability. We say that a value y star is an equilibrium, or otherwise referred to as a steady state or stationary point, of our differential equation, y prime is equal to f of y, if we can write f of y star is equal to 0. In other words, this means that our y prime is equal to 0. So there's no change going on in this population. So an equilibrium essentially means if you are at that point, you stay at that point, but you might not necessarily be at that point, you might be close to that point. So we might want to know whether you move towards that point or away from that point, and that refers to its stability. So we say that a value y star is a stable equilibrium of this differential equation if the limit as t tends towards infinity of y of t is equal to y star for y naught not equal to y star. What this is saying then is if we start at a value close to our y star, so suppose this is our y star here, and this is our y1, well, we want to know whether we're moving towards it. So suppose this here is y2, some other time point, and then we go to y3 and so on. Likewise, if we had started on this side, we would move towards it as well. In this case, if we move towards our y star, then it is a stable equilibrium. The reason why we have this additional condition here, that y naught is not equal to y star, is because we know that if you start at an equilibrium, then you stay there. We want to know what's happening if you are a little bit away from that equilibrium. So this is just saying that if you start near a stable equilibrium, you move towards it. Okay, so that's it for today, but make sure you're familiar with the terminology that we've reviewed, in particular equilibrium and stability, because we'll be talking about them quite a lot. Okay, thanks very much.